really earning my keep here, giving you a second talk. So yeah, I'm going to talk more about the priors now. So it's nice because I can kind of lead off from where I was before. So hopefully there'll be a continuation here in the story. But first, I have to take this opportunity to briefly advertise my group. So I want to point out I have a group now. It's only been a year since I've been at Columbia, but almost a year. But we have a group called the Cool Worlds Lab, or the Cool Worlds team. And I currently have 3 students. Jing Jing's here in the room. I don't know. There she is. Jing Jing's there. Jing Jing's working on population modeling, so if you want to talk to her about that, as well as Angie's fantastic talk I'm sure we'll have later on about that, then make use of that. I just want to point out that if you are thinking about a Sagan fellowship, or you're thinking about applying for graduate school, keep this in mind. Columbia wasn't, we had a kind of a gap where we didn't have anyone work on exoplanets, but now we do. So if you're interested in applying to live in New York and you want to work on exoplanets, then come talk to me. So I just have to throw that advertisement out there. And this is a list of some of the things we're doing, by the way. So population modeling, neural networks, exomoons, exorings, long period planets, single transits, compact objects we're playing around with, some SETI stuff, rocky planet compositions, then all these missions coming up. So if you're interested in any of that stuff, come chat to me about science. But now back to priors. So, it's the same trick. So immediately switch. Okay, so I'll do the same thing I just did. Sagan workshop. I think I'll just grab it off. This is what I always do. Yeah, and then where's the agenda? Yeah. Where's my dates? There, okay. And I need to download this so I can flip between. Can I full screen this? How do I download this?
Control.
Arrow on the next rule.
There's this one.
Symbol upper right, over, left,
Two
left,
buttons
left,
left.
left, down.
Next is the printer.
Down, left.
That one. That one.
There you go.
It's so intuitive.
Does that not work?
We don't have it. Come on. There we go. Sorry about that. This is where you should check your slides before.
Now you go to the green arrow, the down arrow.
I do have to get out of this again. Okay, it's opening. Okay, we'll get there.
I guess I should pause your time.
It's always hard on someone else's system. Okay. View, full screen. Okay. We're back. So I'll skip that. So this is where I was last time, talking about the post-series being a product of the likelihood and the prior. And we're going to really focus in on this prior term. Oh, my video won't play now, will it? Maybe I can just switch to the other one very quickly for a second. Sorry. I have one video and I just wanted to play it, you guys. That's not even the right talk. Did I close that? Is it there? Okay, good. So I want to, before me explaining it, I was going to let my student, Emily Sanford, explain to you why priors are important and how to think about priors. So you're probably sick of my voice already, so I thought she could explain to you. So this is actually a video from our Cool Worlds outreach channel. So we have an outreach channel at our group. It's on YouTube at this address. And sometimes we try and explain things we're working on to the public.
Of times over, you'll find that the probability that you calculate approaches 1/6. So in order to realize this true probability of 1/6, we have to do many, many trials. And in this framework, the word probability can really only properly be applied to repeatable random samplings of this type. So there's another way to think about probability, and it's actually closer to the way that we use the word probability in everyday speech. We can think of the probability of something as our degree of belief that it's true. So we can make probability statements about anything, not just infinitely repeatable random samplings. So we can discuss the probability that an email arriving in my inbox is spam, or the probability that the Orioles will win the World Series, or the probability that the elevator in my building is broken. So this way of discussing probabilities is called Bayesian Statistics. And another interesting thing about Bayesian Statistics is that it allows us to take some pre-existing belief about the state of the world, called a prior probability, and then update it based on some data that we've collected. Then our new belief, which has been revised to reflect the data, is called the posterior probability. So to return to a previous example, when I first moved into my apartment building, I had a prior belief that my elevator would be working most of the time, based on my experience living in the 21st century. However, after a year and a half of walking up the stairs, I've revised that belief, and now the posterior probability that my elevator is working at any given time is very low.
So, much more humorously than I could do it. So, it's kind of like something that it's worth thinking about, that we actually encounter priors and Bayesian statistics like all the time in our lives. We just don't always realize it. So I kind of liked that explanation that Emily gave. Oh yeah, you should check out the channel if you want to get more of those videos, of course. Okay, I have to turn this back on me. No more technical problems. So like for example, think of some cases where a detection claim was made of something like really outrageous and amazing, and the scientific community had a very strong suspicion about it, a very strong prior against it. And then think about whether it turned out right or wrong, whether that prior actually mattered. So, I don't know, I'm going to solicit a request here. Can anyone think of a discovery claim that seemed really like outrageous? And yeah, that's a really good one. Anyone else have a good one that might be? What's that? Okay. Yeah, the Opera experiment. That's a really good one. So, in those cases, we had this prior that the speed of light is a fixed speed limit, that it really can't be disobeyed. We had the prior that we thought Einstein was right because of so many experiments that had gone before. So it was going to take pretty overwhelmingly evidence to overturn that prior belief. And in the end, that evidence wasn't strong enough to overturn that prior belief. So this is why priors are always there, and I think a nice way to think about priors is that extraordinary claims require extraordinary evidence. To quote Sagan, it seems appropriate at the Sagan workshop to talk about that. Really, I guess what he meant was to overwhelm our prior belief. He didn't say that, but it wouldn't have been as eloquent if he'd said that. So that's how I like to think of priors. It's something that we as experienced human beings have about many things. It's just almost our intuition based on life experiences. So it's pretty important in MCMC analyses and Bayesian inference as well, because it is one half of this equation. I like to think of priors as being like on a balancing scale, the likelihood and the priors as being on a balancing act. So your end result, your outcome is going to be the product of these two things. And in any case, one of them is going to be more influential than the other. So hopefully your data is good enough that your likelihood is driving that inference and not your priors. You want this scale to be much, much heavier than this scale. You don't want your priors to be the most important thing. But it's not actually the end of the world. I mean, if your priors do really seem to have more influence on your results than your likelihood, that's telling you something about the quality of your data. So I like to think of it as being, well, it is. I mean, it's not a way of thinking about it. It just is the way to think about it. It's the posterior probability is the product of the likelihood and the prior. And you can think, for example, the posterior is from a low signal-to-noise data. Or really, what I mean by that is low likelihood constraining power, I guess explicitly, would be strongly affected by the prior. So if you had a transit measurement and it just had one or two crappy data points right in the middle with huge error bars, your priors on, say, the impact parameter are going to have an overwhelming effect on what impact parameter you get for your posterior. So in certain cases where you have, it's not necessarily low signal to noise, it also could just be that there's weak constraining power, they're going to have a large influence. But really what you want to be is in this regime, where your priors don't make much difference. But you can't always be in that regime, unfortunately. So some people, as I said earlier on, don't actually like Bayesian statistics. And one of the reasons they often point at it, they don't like it, is because one has to choose a prior, and that somehow detracts from the objective process of doing science. I personally don't see that as a weakness. That's why I like it, because if you change the prior and you get a different result, that's really important information. That's a strength, not a weakness of this method. So as long as your priors are reasonable, I mean, you don't want to choose, call them pathological priors, like a delta function, then obviously that's going to, whatever your likelihood is, that's going to overwhelm it. But if you choose between several reasonable priors, as Eric mentioned earlier, try 5 different reasonable approaches, and if you get the same result, then you can have some more confidence in it. The other thing you can do with priors, which is kind of useful, is do something called Bayesian learning, where the outcome of your last experiment, your posterior, can become the prior for your next experiment. So you can propagate knowledge in this way using priors. That's, I guess, an informative prior in that case. So if we go back to this picture I showed earlier, we're really focusing in on what this box down here is doing, the priors box. And you have to, this is sort of my cartoon breakdown of how to choose a prior and how to implement a prior. And I'm going to focus on these 3 different techniques. Actually, I'm not even going to focus on this one too much. Uninformative priors, informative priors, conjugate priors that we heard about in Jesse's talk. I'm not going to talk about hierarchical priors or hierarchical modeling because we're going to have a talk on that later from Angie on Thursday. So definitely stay tuned to get the final piece of the puzzle on that. So I'm really thinking about non-hierarchical cases here. Conjugate priors, we've heard a little bit from Jesse about that. I'm probably not going to, well, I'm not going to talk about that too much because it's actually rarely used practically in exoplanet work. I think, in my opinion, it's mostly useful for analytic work, so I'm actually using it myself in some analytic. I like deriving analytic posteriors, and if you're doing that, then this is perfect. But practically speaking, if you're running an MCMC, which is a numerical method, you're going to be doing either this or this, and probably most of you will be doing this most of the time. And then finally, how do you actually implement the prior, which is kind of a key thing. You know, we talk about priors, and you're like sat there thinking, well, okay, that's all great, but how do I actually do that? So I'm going to actually try and break that down a little bit in the second half here. Okay, so let's talk about uninformative priors. These are by far the most commonly used priors, I think, in exoplanets. So probably the first thing to say is a bit of a nismer. There isn't really such a thing as uninformative. Any prior you choose has information in it. You're just really trying to choose the least informative prior when you do that. So sometimes they're called objective priors instead of uninformative priors. But by and large, when you read AppJ papers and MNRAS papers, people tend to use this language of an uninformative prior. The simplest rule might be just the principle of indifference, and that's basically saying every single trial, every single theta guess is as likely as any other is my prior, which is a uniform prior. The key thing with the uniform prior is you have to define an A and B. People don't often realize this, but you have to define a minimum and a maximum of the uniform prior. You can't let this be minus infinity and plus infinity. Okay, otherwise, I mean, practically speaking, you kind of can, and I'll come to that in a second, but formally, you have to actually define a finite value for A and B. So that comes to the point that often exoplaneteers do technically use what's called an improper prior, which means that probability distribution doesn't integrate to 1 over the entire range. So formally, even though it's not stated in the paper, it's not even in their code, that they are kind of implicitly using an improper prior. And really what they're doing is they're letting the MCMC go anywhere it wants, and it has equal probability to go anywhere it wants. So it's purely just like using just delta chi-squared or delta likelihood to evaluate whether to accept steps. That's actually not wrong. It's not terribly wrong to do that, though. It's generally actually okay. And that's because if you are using uniform priors, then the probability of the transition, if you have no likelihood, is 0. It doesn't depend on A and B in any way. So practically speaking, what you're kind of doing is assuming A and B are just really, really large numbers. They're not infinity, but they're just really, really large numbers. It doesn't really matter. They're just way, way outside your box. So if you're doing one of these two, practically speaking, you are using sort of these, what I call maybe unbounded uniform priors implicitly. And you do see that quite a lot. But it's not necessarily wrong. However, in most cases, you can write down what the lower and upper bound of your parameters are. So you may as well do that. It's kind of wasteful for your MCMC to be exploring negative radius planets, right? I mean, you know what the bound is. It has to be a positive number. Like, why are you letting your MCMC return not a number over and over again doing that? It's just going to cause problems. So you may as well use that prior, set a prior. You do actually have information. So some examples like eccentricity. You can't have a negative eccentricity, obviously. You can have E greater than 1, but it just won't be a periodic transit, or a periodic orbit, or just, it's basically swinging around the star. You can have ratio of radii. I usually use the symbol P for that. Use whatever you want, but of course that's usually got to be greater than 0 by many definitions. I normally would cap that at being less than 1, just as a practical thing. I'm saying the planet can't be bigger than the star. That's, of course, not always true. If you're doing EB work, then you want to use a different prior to that. That wouldn't be a good prior to use. You would bias yourself if you did that. And finally, like a parameter like A over R star, you have a lower bound here that you know the planet can't be inside the star, which means that A over R star has to be greater than 1 over P. So many cases, many parameters in your problem, have a think about them. I bet you can write down at least one hard limit as to what it shouldn't be able to do. So sometimes you can I said you can't have a negative radius planet, but sometimes actually we do trick our algorithms to do that deliberately. So for example, you could let the ratio of radii go between -1 and +1, where, of course, negative radius, physically speaking, means nothing. What the hell is a negative radius? But in your code, you can just code it up that it creates an inverted transit instead of a normal transit. So this is sometimes useful if you're not sure, if you have a very significant signal, it's like right on the edge of detectability. And if you just have a bound at 0, then your MCMC walkers can't jump to negative space if I have a uniform prior set on 0. So what's going to happen is the true posterior might want to do this. It's a complete null detection. But because of your bound on 0, you end up with a positive bias like this. So your posterior ends up getting slightly pushed into the positive because it can't go negative. The walkers can't go negative. They always get rejected there. So you can sometimes end up with these slightly, when you plot your histograms of your posteriors, you can see this peak, and you shouldn't necessarily put too much faith in the strength of that peak. It's actually pretty well known, especially for eccentricity. So for eccentricity, there's many papers that have pointed out this problem. Eric Ford among them over here. I think even back in the 70s, Lucien Sweeney was writing about this. Lots of people use the so-called Lucien-Sweeney test still to evaluate that. A good trick to help you get around this is to reparameterize the problem. So instead of thinking for eccentricity, which it has this hard limit of negative, you can't have a negative eccentricity, you can try E sine omega and E cos omega instead. Or here I've done E to the half sine omega and E to the half cos omega. And those parameters can go to -1 to +1. And then in your code, you would evaluate what eccentricity is as just being the sum of the square of these two. And then you have your eccentricity. And when you plot your eccentricity histogram, it won't be as affected by this boundary condition. By the way, if you do nested sampling, just to sell nested sampling to you, you don't have this problem at all. It's not an issue. So this is one reason why I don't like MCMC that much. So here's one thing you might want to do before choosing a set of parameters and essentially priors that you're fitting for. If, for example, I chose E sine omega, E cos omega, then let's generate what the prior on E looks like. So if I assume a uniform prior in these two, between -1 and +1, so I'm just generating random variates from a uniform distribution between -1 and +1, I do that 10 to the 5 times, and then I plot the sum of the squares square rooted, which is the eccentricity. That's what your eccentricity prior is. That's what you're basically assuming. So you're assuming sort of a linear prior on E. So that's why that can be true. It's not the end of the world. You can actually correct for that by later on, as we'll talk about how to implement priors with a log likelihood penalization technique. But it's kind of silly. It's kind of annoying to be fitting for a parameter that's doing that. So if you do E to the half and instead, you get a nice uniform distribution. So this is a good thing to check out. If you're transforming between parameters in your code, then just check out what the priors actually look like on those transformed parameters first, before assuming them blindly. On a related note, but I'm not going to talk about this too much in the paper, but there are also certain proposal functions which you might think about, or reparameterizations essentially, which can optimize minimize the covariance structure basically when you're walking around likelihood. So that basically makes the MCMC much, much faster because it doesn't have those like banana-shaped correlations. So a couple of good references for that are Carter 2008, Josh Carter's paper on transits, and Eric Ford's paper on RVs from 2006. There's many like good suggestions of reparameterizations which will make your MCMC more efficient. But always do think about what the prior is that you're getting out as a result of that. I guess technically many of these things are kind of irrelevant if you're using MC. Maybe I would disagree with that, but I don't know. If you have a really smart sampler, then it's not so much of an issue. Another very popular uninformative prior is the log uniform prior. So we had uniform before, this is now log uniform. And this is pretty good when you have a parameter that's scale-like and it scales orders of magnitude. So for example, the radial velocity semi-amplitude could be anything from 10 centimeters per second up to a kilometer per second. So you're spanning many orders of magnitude. If you use a uniform prior, you might not be exploring the full parameter space as efficiently doing that. Period, for example, you might do it with, and these stellar density, AVR star, they're sort of typical parameters. You might think about doing a log uniform. Mid-transit time, just make this specific to transits, and I guess similarly time of conjunction when you're fitting inferior conjunction, when you're fitting radial velocities. That's really a location parameter, it's not a scale parameter, so even though it does have a large range potentially, maybe orders of magnitude is kind of in a way it could go for anything from 0 to 100 days. I would still use considering it as a location parameter means you should use a uniform prior if you want to use an uninformative prior. So a general rule of thumb is that if you have a location-like parameter, you use uniform. If you have a scale-like parameter, try log uniform. Okay, so there are some issues though with log uniform, and one is that you can't sample near 0. I can't set x min to be 0, otherwise this thing explodes up to infinity. So technically it's an improper prior if you want to go to 0. So if you want to get down to k equals 0, that's a problem. But normally you could just say k 10 centimeters per second is the smallest RV signal I really care about. However, if you really do want to get down to 0 and you really need to get down to 0, you can use a modification to this, the modified log uniform prior. Which was in Ford and Gregory's paper, and it was also part of ExoFit by Balan and Lahav. So it's a fairly popular parameter for things like, again, K. It tends to be fairly popular. And jitter, if you're fitting for jitter in your RV, sometimes this is a popular parameter. So these are just giving you like a taste of some of the most commonly used uninformative priors. I think that pretty much sums it. Uniform, log uniform, and modified log uniform are pretty much the 99% uninformative priors people are using in exoplanets. So to summarize that, when you're doing uniform, think about your boundary conditions carefully. Check your priors on key parameters via Monte Carlo tests, bootstrapping basically. And log uniform priors, think about those for parameters which scale orders of magnitude. But with log uniform, what you're really saying is, I should have said this, you're saying I don't even know the order of magnitude of this number. Not only do I not know the number, I don't even know the order of magnitude of that number. That's kind of what you're saying. That's why people call it more uninformative. It's kind of a strange word to say, but so let's talk about uninformative priors, the opposite of this. So I guess the obvious example is Bayesian learning that we mentioned. So you could start with some data, and you have some prior. Your initial prior, let's say it's a uniform top hat like this, and I derive some posterior distribution. And I could use that posterior, that red line, I get some new data, and I can use that as my prior in the next experiment. So imagine you, let's say, measured 5 transits from Kepler, and then you had a 6th transit. Rather than having to refit all 6 transits together, you could use the posterior from your fit from that Kepler 5 and use that as a prior when you fit your 6th, which might be a ground-based measurement. For example, that might be something you use this for. Practically speaking, it's not done very. In fact, I don't think anyone really does it in exoplanets. Exoplanets almost always just refit everything, which is equivalent to doing this essentially. It's kind of more work computationally, but this is a lot of work mentally actually to make this work. And the big reason is because this is a posterior I showed earlier. Good luck sampling from that. It's not easy to sample from these distributions, and it's often more efficient, actually, practically speaking, just to refit everything. So be aware that it's a concept that exists, but you probably won't be using it too much. I think it could be useful, Bayesian learning, for scheduling of telescopes and resources. So yeah, I'm happy to talk to you guys, bounce ideas about that later on. But I think there could be something interesting to do with Bayesian learning, but maybe not for this kind of case where you're trying to fit parameters. So informative priors, another type of informative prior you might use is an observed distribution. So for example, someone shows you, this is much more convincing when I could do the transitions, but anyway, if I show you some RV data, let's say these points are some RV data, and these two curves, a circular orbit curve and a eccentric curve, give exactly the same likelihood, or nearly the same likelihood. And I said to you and I show this to Deborah, or I show this to someone who's very, very experienced at looking at RV curves, and I say, which of these do you reckon is more likely? I bet most people, maybe I misspeak, would say the circular orbit case is probably more likely, especially if this eccentricity is really, really high. You just have this inbuilt suspicion because we know from looking at lots and lots of exoplanets that circular orbit planets are more common. This is a histogram of all of the exoplanet eccentricities from radial velocity. So you'd be right. Your intuition, based on years of looking at many, many planets, is that circular orbits crop up more often than highly eccentric orbits. And you can build that wisdom in. That sage wisdom of the seasoned observer is formally built in by using an informative prior. So again, it's this idea that we talked about as being a very sort of common sense concept. That's what a prior is really doing. It's tuning in that information. So in this case, this is a distribution. This is a beta distribution, actually, in this case. One thing you have to be careful with is using this distribution, which has been measured from radial velocity planets. I can't use that on directly imaged planets, or I can't use that on transiting planets. Those planets were detected using different techniques. They have different observational biases. So therefore, this distribution of the transiting planets is actually going to be a little bit different. And for a directly imaged population, they're much, much longer period planets. You definitely can't say that the sample you've calibrated on is going to be representative. So the point is, be careful. If you use an observational prior, make sure you're using it from a sample set which is representative of the sample set you're trying to apply it to. Or you can, as I'm about to explain, try and correct for these effects. And you can have some success doing that. So for example, here's the effect of transit. So let's say we've calibrated some eccentricity distribution based off radial velocities. But we know, and I'm going to use a beta in this case as I used before. It's not the only one. There's many, many ones. This is not the right one. There's many ones. I just like this one. It's convenient. The effect we have to consider, though, is that transiting planets are more likely to be eccentric than your typical planet. So this isn't obviously intuitive. You probably all know that a planet which is closer to the star is more likely to transit than a planet which is far away, right? It's just easier to line them up to get that transit to occur. But the same thing actually also happens to a certain extent with eccentricity. So there's a couple of papers, a reference back here, Barnes 2007, Chris Burke 2008, which really pointed this out to the community when, I guess, just before Kepler launched. And this is kind of a subtle point, but if you sort of take the average of phase over a highly elliptical orbit, it spends more time closer to the planet on average than it does. And by time, I really mean phase, not actually time on its orbit. There's more phases where it's closer to the planet than it would be if it was on a circular orbit of the same major axis. So because it's phase, on average over phase, it spends a little bit more time closer to the star, the transit probability gets boosted up a little bit. So that means that the population I take a random transiting planet versus a random RV planet, the transiting planet is more likely to be eccentric than the RV planet. So that's what I mean by different detection biases. So you have to keep that in mind if you're going to try and cross-translate different priors. So you can, in principle, correct for this effect using conditional probability theory. So let's say the probability of E and omega, two parameters I might care about, given that, conditioned on a planet is transiting, that's what I'm using there as my symbol to define a planet is transiting, is going to be just the original prior, P of E and omega, multiplied by this probability that Barnes and Burke worked out. That's it. And there's a normalization constant, but essentially that's it. So you get this horrible looking equation. It's not very intuitive what it's doing. So let's actually do some plots. That's always what I do when I get an equation. And kind of what it's doing is this. So we start out with some initial eccentricity distribution, and it's getting slightly modified. So if I know let's say this is the RV population, that red line, the pink line. The transiting planets, if they were drawn from exactly the same types of planets, should actually follow a different distribution just because of geometric bias, basically. So you'll find more eccentric planets, the blue's a bit higher, high eccentricities, and less circular orbit planets. That seems like a small effect visually on there, but if I plot it as a function of omega, you can see how important it is. So omega is the argument of periastron. We assume all planets in the universe are just randomly oriented. There's no preferential orientation for solar systems. So it should initially just be, P of omega should just be a uniform prior. But if I know it's transiting, it's much more likely to be caught near periapsis than it is at apoapsis, because apoapsis is when it's furthest away from the star. That makes sense intuitionally, and I did have a video, but obviously it's not going to play, but essentially what would happen is that as I pump up the eccentricity, this blue line would become more and more sine-like. It'd start out kind of shallow, and it'd become more and more sinusoidal until it was almost touching the bottom axis here. So you do have these strong biases in these terms that you have to be aware of. So what's happened is we've gone from this joint prior to this joint prior. Okay, so now this has covariance structure. You can see that in the shape of this. So these are some of the more subtle points. So if you're using observational priors, there are many caveats. Let's say you're fitting single transits. A lot of people are interested in single transits right now, and if you're trying to infer the period, that's completely degenerate with the eccentricity. So if you don't choose a good eccentricity prior, you're going to get completely the wrong result, or at least a skewed result or a biased result. It's not going to be the right result. Okay, so this actually gets even more complicated. I won't go too much into this, but there's even, apart from geometric bias, there's also detection bias, which together form observational bias. So detection bias is, for example, an apoapsis transit, a planet transiting near apoapsis, is moving slowly at that point in the orbit. So therefore the transits will last longer. And a longer transit has a higher signal to noise than a very, very narrow transit, because it goes a square root of the duration, basically, the amount of signal to noise I get. So that also biases you a little bit. And actually it turns out it almost deletes the previous prior. So actually it flattens things out with omega, which is nice. It really suppresses this bias. Because this was kind of weird. If you made a plot of omega histogram on exoplanet.org, you wouldn't see such a skewed distribution as this. So the detection bias effect actually explains why it's not as skewed as this. So these effects are real. They're affecting our data. Okay, I should also point out we don't know any of these effects for radial velocities. At least I'm not aware of any paper which has formally derived these biases in this way. There are definitely biases. They're probably impossible to write down completely analytically, because radial velocity observers have their own mentality as to how they choose targets and which ones they follow up. So it's going to be very, very difficult to write down an equation to describe that. But in principle, we don't actually know what that bias is. So just to summarize that, this is okay. You can take, or it can be okay, it's not necessarily okay. You can take the eccentricity distribution of RV planets and apply it to fitting some RVs. If that planet you think is a typical member of the planet population in which you calibrated it from. But you can't take that distribution and apply it to transits or direct imaging, unless you're going to think really carefully about these effects. Okay, so any questions on this before I move off? Particularly at the end. Okay. So that's informative priors. A little bit dense, but we have, just to summarize that, we have techniques like Bayesian learning that you might want to think about using, but practically speaking, probably not when you're trying to infer parameters that much. May as well just refit everything. Observational experience kind of defines what we're doing when we use informative priors, or at least often it does. And when you use observational priors, just be really careful when you apply them between different techniques. Okay, so I'm going to move on to how to implement a prior. How are we doing on time? Okay, that's all I need. So this bit's pretty quick. So to implement a prior, there's a couple of ways. Log likely penalization is by far the most common way. I'll point out that you can do this as well. It's far less common, but it does work. But first, let's talk about log likely penalization. Let's write out this posterior probability again. So it's P of theta given some data, given a model, prior times by a likelihood. If I do the log of that, which is normally what we like to work with to be numerically stable, then you can see that essentially the log likelihood has just had added onto it the log of the prior probability. So you calculate what your prior probability is, take the log of it, and add that onto your log likelihood. And you can kind of think of that as your effective log likelihood, or your sometimes call it log likelihood penalization. Really, you're just calculating the log posterior probability. So this is pretty much the easiest way to add it on. It's nice because you can do this for not just univariate priors, but sometimes, as I showed earlier, you might have covariant priors, and this still works pretty nicely. So that's by far the most popular way. As a really simple walkthrough example, if I had a Gaussian prior on a parameter, I take the log of it. The PDF looks like this. So unless you want the evidence, you don't need to really worry about these constant terms. Just ignore the constants. Your log prior probability is just going to be basically 1 minus half of x minus mu squared over sigma squared. So the highest prior probability occurs when x equals mu, as you might expect. So the prior is drawing it towards the center of the Gaussian prior in that case. So you just literally add that on. So it's a minus sign. So remember, you add that onto your log likelihood, and you're done. So I'll briefly mention another technique that is kind of nice, but technically it's kind of hard to implement, but it has advantages. Inverse transform sampling. Far less well used, but kind of a case where you might be interested in doing this is if you had a parameter space that looked like this. So I had some likelihood function, and I had some prior. It's kind of exaggerated, but you might have a prior which is just really strange, and you only want to, of course, sample from the convolution, the Venn diagram overlap of these two regions. That's really the region you're trying to sample. Now, if I'm just doing normal samples, it's very inefficient because, again, we have this sort of narrow region. But the likelihood itself is nice and broad. So it's just the prior that's really screwing us up. So we could just compute the log likelihood penalization and reject a heap load of trials, and eventually it will converge, but it will take a long time. Or you can actually just draw samples from the prior itself, which is the idea of inverse transform sampling. And you really need to walk in that parameter. You can't just do, in NumPy, random dot normal or whatever your prior is. You can't just do that. You have to actually walk in that parameter, otherwise you're not forming a Markov chain. And that's the idea behind doing this. So to give you a bit more on this, so what we're doing when we do inverse transform sampling is we're really thinking about the CDF, the cumulative distribution function of our probability density. So this is the PDF of a normal, that's its CDF. You'll notice that it always peaks at 1, it flattens off at 1. So it has to, by definition, if it's a proper prior. That means the integral at the maximum bound is equal to unity. That's what you want for any proper prior. So essentially what we want to do is if we just take random samples along this axis, this is my CDF, and this is the cumulative probability. If I just draw random samples along here from a uniform distribution, and I draw a line back down, I kind of solve the inverse of the CDF, basically. It's sometimes called the IDF, the inverse density function, but it's the inverse of the cumulative density function. I will return back a Gaussian prior, a Gaussian probability distribution. So that's kind of the idea. If you just throw samples along the CDF line, and it comes back down your parameter variable to give you the distribution you want. But that's just generating completely random samples. That's not walking. But you can walk. You just walk along in this space, essentially. So I just make a jump along this axis, and I'm now walking between 0 and 1. And if there's no likelihood function, the limit of absolutely no data, where I'm not constrained at all, then it will just basically walk up and down in a uniform distribution, and that will return the prior as expected for the case of no likelihood. So this is the idea behind inverse transform sampling. It's very advantageous because every sample is drawn from the prior. You don't have to test whether it's drawn from the prior. It is drawn from the prior by definition. But it requires that you can invert the CDF. So if your CDF is a horrible equation, a really messy, disgusting equation, or it's not even analytic, that can be problematic. Or if it's not univariate, it's bivariate or multivariate, that can be really hard as well. You have to do that in a conditional way, which I won't talk about. But it can be tricky. But in some cases, it can be very advantageous. So if you have hundreds of parameters in your model, and normally what would happen is you have a prior in every single one. Many of your samples are going to be very inefficiently exploring the parameter space just because of the effect of the prior. But if you did inverse transform sampling on those hundreds of parameters, you would be much more efficiently exploring parameter space. So this can be advantageous. Okay, so, but as I said, there are some issues with it, such as it's hard to do, basically. Mentally, it's hard to do. You have to invert these distributions. Some packages, such as, the reason I point it out is some packages such as multi-nest, which is not an MCMC code, it's a nested sampling code, exclusively sample using inverse transform sampling from the priors. So you should be aware of it because some packages only do that. They don't do anything else. So you can still add on a log-likelihood penalization if you want to, but you shouldn't do both, actually. You shouldn't penalize both with a log-likelihood and inverse transform sample. Or you're sort of double prioring yourself if you do that. Okay, so it's optimally efficient for exploring the prior volume. It's the default for some codes like multinest. And it's hard if you have non-standard distributions, so just be aware of that. So I'm just going to leave I think I have 2 slides. So just this last couple of slides. This is just like some suggestions of priors you might use. There's no right answer. I would definitely not treat this as this is the cheat sheet of priors to use in all cases. But these are just like some typical suggestions that I might think about using when I fit data, just to give you guys some ideas. So, log uniform for period on transits, uniform for the ratio of radii, or log uniform either are fine. Impact parameter's got to be uniform. For eccentricity, I tend to use something more informative because a transit really doesn't constrain eccentricity at all, unless you know the cell density. So you have to kind of have some prior on it, otherwise it's just going to go everywhere. Which actually sometimes you want it to go everywhere, but if you don't want it to go everywhere, you need to put something more informative down. Limb darkening, I have some backup slides, they're online, all about how to do limb darkening. I don't have time to talk about it, but limb darkening is tricky, but there are nice ways, parameterizations you can do to solve that. Then RVs, here's some suggestions, actually mostly from Eric, so talk to Eric about those. So yeah, I'll leave it there, and you can check out my extra slides online. I personally wouldn't. The ratio of radii, for example, in that case, it can be quite degenerate with impact parameters. So if your data is like really flat bottomed and you can really see it's definitely not a grazing event, it's maybe okay to do that. But sometimes, especially if you have with Kepler data, there's a smearing effect in the long cadence data, which sort of smears out. It's really hard to tell if that one transit you're looking at is actually maybe close to grazing or near grazing. And in that case, the size of the planet has to be much, much bigger. Because if they're barely overlapping, then this planet could be really large in that case. So therefore, you need a prior which can go all the way up to the top in that case. So I certainly would say it's fine probably to seed your MCMC from your best guess, and it hopefully will stay there. But there's really nothing wrong with letting your priors be large. There's no reason not to do that. Otherwise, you're restricting yourself unnecessarily in terms of the answer you're going to get out. Am I worried about how to choose the priors?
Quality of your science results and those of all the other people who do this.
Yeah, I think generally a good thing to do is to try, as you said earlier in your talk, is to try multiple results. Actually, when I was first learning basis, that's the first thing I was taught by Ofer Lahav at UCL. He said the first thing you should do is try a few different reasonable choices and see if you get the same result out. So that's actually the common argument, right? Why people don't like Bayesian inference, because there's that choice, and it does affect the science result, unlike what I said in the first talk. So you should worry about it. You should try different things. In some cases, if you can like eyeball, let's say, a result. Let's say you have a straight line or something, and you can just see the data's like has no noise. It's just perfect on that line, or transit's just perfectly beautiful. You probably need to worry less, I'd say, about your priors in that case, because by definition, the likelihood is overwhelming the prior in that case. I think you have to use your intuition a bit, but if you're in a weakly constrained problem, you should worry about your priors. You should spend time thinking about it, and you should try different things out. If you're in a super well-constrained problem, you've stacked 1,000 hot Jupiter transits on top of each other, and it's just like looking at an HD light curve. You probably don't. It's not going to make that much difference whether you use uniform or log uniform in those cases.
Really quick, thanks, David, again.